Introduction. Structural equilibrium demands that internal reaction load in the cross-section be resolved into a resultant force and resultant couple. The balance between the external force and internal force is maintained through the generation of bending moment and shear force. In this experiment, we explore the dynamic relationship between external load, internal reaction, and resultant bending moment. The internal reaction manifests as a shear force and bending moment, which are critical components of structural design. The aim of this experiment are 1. To measure the bending moment of material when subject to different load at different distance. Second, use different load which are 0 Newton, 10 Newton, and 20 Newton. Third, the distance P1 from point A are 100 mm and 200 mm. The distance P2 from point A is 300 mm and the distance P3 from point A are 600 mm and 700 mm.
Statics is a branch of physics that studies objects in equilibrium, so a key concept in statics is the bending moment, which measures how much a structural element, like a beam or a bridge, bends under external force, as depicted in Ultimate Guide to Shear and Moment Diagrams 2024. So the relationship between bending moment and shear force is defined by specific equations, which show how changes in shear force affect bending moments. So bending moment in diagrams help visualize where and how the bending occurs along the structure, aiding our understanding of the forces at play and ensuring the design can withstand these forces without failing. So figure 3 shows the equilibrium of moment analysis, and the other shows the load, which then can be translated into shear stress and bending moments. This one shows for the uniform load. For vertical equilibrium of part A, there must be a shearing force QC acting as shown in figure 4, and this is equal to negative RA. So this force counteracts the reaction force RA at the support to maintain the equilibrium. So for vertical equilibrium of part B, the shearing force QC acts as shown and has the value of positive RA minus P, whereas P is the external load applied. So to accurately determine the result, a sign convention must be used. The typical convention is shown, leading to the negative values as above. So this ensures consistent analysis and helps in correctly interpreting the direction and magnitude of the forces involved. So this figure shows the experimental setup, and the apparatus to be used in the experiment is for the experimental beam, load, and load hanger.
Methodology. Beam support RA was set at point A and the beam support RB was set at 300 mm away from point A. Load hanger P1 was set 100 mm from the fixed hanger P2. Load hanger P3 was set 400 mm away from fixed hanger P2. Part A and Part B of the beam was aligned by adjusting the spring balance until a bubble in the balance was at the center. National reading of the spring balance for balance reading when load is 0 was recorded in Table 1. 10 Newton of the load was placed on the load hanger P1. The beam was realigned and reading of the spring balance was recorded at Table 1. The 10 Newton load was removed from load hanger P1. Step 5 and 6 was repeated for fixed hanger P2 and load hanger P3. Step 5 and 7 was repeated using 20 Newton load. Step 3 to 8 was repeated by setting the load hanger at P1 100 mm away from the fixed hanger P2 and load hanger at P3 300 mm away from the fixed hanger P2.
Result. The table below shows that the balance reading at distance of 100 mm, 200 mm, P1 from point A, 300 mm, P2 from point A, and 600 mm and 700 mm, P3 from point A, with three different load, which is 0 Newton, 10 Newton, and 20 Newton. To get the net force for load at distance of each point, we will minus the value we get from 10 Newton and 20 Newton minus the value we get from the 0 Newton. Discussion. To get the measure bending moment, we must do calculation by using the formula below. Measure bending moment equals to net force for load times level arm, which is 150 mm. So the table below shows that the result that we get from the formula. To get the theoretical value of bending moment for each point, we must calculate the reaction at point A and B first. For example, the P1 at distance of 100 mm from point A, the total moment at point A equals to 0. Because of the P1 is go downward, so we put the negative in front P1, which is negative P1 times L1, 100 mm plus RB times LB equals to 0. So negative 10 times 100 plus reaction B times 900 millimeter, which is the distance from A to B, equals to 0. So we will get the value of RB, which is 1.111 Newton, and repeat the same step to get the reaction A, and we get the value of 8.889 Newton. We will repeat the same step for the next point. We just switch the value of distance of LA and LB, and we will repeat it with different log. So this is the result of theoretical bending moment for this point. We will calculate and plot the bending moment at the distance of 300 millimeter for each cases, and the 10 Newton and 20 Newton will share the same graph but with different value for every point. This is the result of theoretical value of bending moment for each point with two different lots, which is 10 Newton and 20 Newton, after the calculation and sketching the graph. The comparison between the bending moment value obtained from the experiment and the theoretical calculation can be done by calculating the percentage error for the experimental value of bending moment. The percentage error for the value of bending moment obtained in the experiment can be calculated by using the formula shown below. Percentage error equals to modulus experimental bending moment value minus theoretical bending moment value over theoretical bending moment value times 100%. The table below shows that the percentage error between measure and theoretical bending moment at 100 millimeter. We will show the result later in different points, which is 200 millimeter, 300 millimeter, 600 millimeter, and 700 millimeter. According to the tables above, the highest percentage error recorded is 20.01% when a lot of 10 Newton placed on a lot hanger P3 at distance 600 millimeter from point A. There are a lot of errors occur during the experiment that causes the difference between the experimental value and theoretical value of bending moment. Firstly, a scale reading of spring balance is one of which will affect the accuracy of the data that obtained from the experiment. Other than that, the parallax error also occurs when the observer was taking the reading from the spring balance, will contribute the inaccuracy of the data obtained. Lastly, the load hanger will swing after being located at certain position when there is a disturbance such as wind and table movement. The load hanger to be out of position when the load was placed on it. To reduce the percentage error that occur in this experiment, the load hanger and fixed hanger need to be stabilized before putting any load on them. Next, the fan needs to be switched off to minimize the distribution of wind towards the experiment setup. The observer should be make sure that the eye level is perpendicular to the scale reading of the spring balance.
So the conclusion is the experiment investigated the relationship between external loads, internal reactions, which is shear forces and bending moments, and their effects on a structural beam. So despite encountering some errors like worn-off scale readings, parallax during the measurements, and swinging load hangers, the data provided relevant insights. So the highest recorded percentage error in this experiment was 20.01% when a 10 Newton load was applied to a load hanger P3 at 600 millimeters from point A. So to increase the accuracy in future experiments, we need to stabilize the load hangers, minimizing the disturbance and ensuring precise measurement are crucial so that reliable structural analysis can be obtained.
Safety procedure. Personal protective equipment (PPE). Ensure all the group members wear appropriate PPE, including lab coat, safety glasses, and gloves throughout the experiment. Second, load limit. Adhere to the specific load limit for equipment and material. Do not exceed the recommended capacity of any equipment. Third, material handling. Ensure handle the load with both hands, using proper lifting technique to reduce the risk of drop, damage, and injury in the material laboratory. Fourth, secret feature. Ensure that the experiment beam, plate hanger, and fixed hanger are secure fastened in the place before applying any loads. 5. Equipment inspection. Regular inspect and maintain all equipment used in the experiment to ensure it is in a good working condition. Report any malfunction or damage promptly. Lab environment. Keep the work area organized and free from unnecessary obstruction. This is the reference that we use in this experiment.